Welcome to Across the Globe. Today we will learn about Introduction to Neural Networks. Neural networks are algorithms inspired by the human brain, adept at pattern recognition by interpreting sensory data. They process raw input through machine perception, enabling tasks such as labeling and clustering. Their strength lies in identifying patterns, predicting outcomes, and deriving solutions from data. For example, in finance, neural networks can analyze historic stock prices to predict future trends, showcasing their ability to generalize patterns for practical use. Neural networks utilize layers of interconnected nodes, neurons, to process input data. The input layer receives initial data, hidden layers process the data, and the output layer generates the final result. Adjusting the weights of connections between neurons during training optimizes the network's performance. For example, in image recognition, a neural network's layers process pixels to identify objects in images accurately by adjusting connection weights in recognizing patterns effectively. Activation functions play a crucial role in determining the output of a neuron in a neural network based on the input signal received. Examples of activation functions include sigmoid, tanh, ReLU, and softmax. The selection of the activation function can significantly influence the learning efficiency and overall performance of the neural network. For instance, ReLU is commonly preferred in hidden layers for deep learning tasks due to its ability to mitigate the vanishing gradient problem, while softmax is frequently used in the output layer for multi-class classification to generate probabilities for each class. Understanding the characteristics and appropriate usage of different activation functions is essential for optimizing neural network architectures to achieve desired results in various machine learning applications. Neural network training process involves input data feeding, output to expected result comparison, and weight adjustments to minimize errors. Backpropagation algorithm is widely utilized for weight updates based on training error. Neural network training necessitates abundant labeled data and substantial computational resources. For instance, training a network to recognize handwritten digits entails feeding it images of digits along with correct labels and adjusting weights to minimize errors, improving accuracy over time. This process demands significant computational power and ample annotated data for effective model learning. Neural networks find practical usage in tasks like handwritten digit recognition, exemplified by the MNIST dataset. By utilizing the Keras library in Python, a neural network can be constructed for this purpose. The given example demonstrates the process. 1. Import necessary modules from Keras. 2. Create a sequential model. 3. Add layers to the model using the dense function, specifying the number of neurons, activation functions, and input shape. 4. Compile the model using an optimizer, loss function, and performance metric. For instance, in recognizing handwritten digits from the MNIST dataset, comprising grayscale images of digits ranging from 0 to 9, the neural network is constructed with layers for input features and outputs representing each possible digit. Through training, the network learns to associate pixel patterns with specific digits, enabling accurate digit recognition based on input image features. Neural networks are adept at recognizing patterns and making predictions. To effectively create and utilize neural networks, comprehension of their fundamental components and training procedure is crucial. Python provides accessible resources like TensorFlow and Keras, streamlining the process of neural network development. These tools empower developers to efficiently build robust models for varied applications, ranging from image recognition to financial forecasting. A neural network is like a complex interconnected system of pipes that guide water flow in different directions. The input layer is like the source of water, where data is introduced into the system. The hidden layers are like the pipes and pumps that manipulate and process the water flow before reaching the output. The output layer is like the destination where the final result is observed. Each node in the network is like a valve or filter that controls the flow of information. By adjusting the weights and biases of the nodes, we can optimize the flow of information through the network, just like adjusting the pipes and pumps to optimize water flow. Implementing a neural network in a program involves creating these interconnected nodes, adjusting the weights and biases, and processing the input data to produce accurate output results. Hey, Code Conquerors, ready to level up? With TechLearn ATG, showcase your skills with official course certificates. Just visit our site and start. Need that extra boost? Get tailored learning, 24/7 support, and expert guidance. Coding smarter, growing faster, and making learning fun. Go to our website across the globe, www.atg.world. The provided Python code implements a simple neural network with an input layer, a hidden layer, and an output layer. The network performs forward propagation to calculate the final output based on the input data and the defined weights and biases. The sigmoid activation function is defined to introduce nonlinearity to the network by transforming the input value into a probability-like value between 0 and 1. 2. Input data consisting of three values 0.2, 0.4, 0.6 is initialized. 3. Weights and biases are initialized for the connections between the input and hidden layers, as well as the hidden and output layers. These parameters control how information flows through the network. 4. The forward propagation process starts by calculating the input to the hidden layer through a matrix multiplication of the input data with the corresponding weights, followed by adding the biases and applying the sigmoid activation function to obtain the output of the hidden layer. 5. The output of the hidden layer serves as the input to the output layer. Similar matrix multiplication with the weights connecting the hidden and output layers is performed, along with the addition of the output layer bias. The final output is then computed using the sigmoid function. 6. The network's final output is printed, representing the network's prediction or decision based on the given input data. By executing this code, you can observe how a neural network processes information and produces an output, demonstrating the fundamental principles of neural network operation. In real-world applications, this neural network setup can be utilized for tasks like binary classification, where the network learns to make decisions based on input features to distinguish between two classes, such as spam detection in emails or sentiment analysis in text data. Neural networks are widely used across the globe in various industries for tasks ranging from image recognition to natural language processing. For instance, in the field of finance, neural networks are utilized for fraud detection. By analyzing patterns in transaction data, neural networks can flag suspicious activities and help prevent fraudulent transactions. Another industrial application of neural networks is in the field of healthcare for medical diagnosis. Neural networks can be trained on a large dataset of medical images or patient records to assist doctors in diagnosing diseases, predicting outcomes, and recommending treatment plans. These examples highlight the versatility and effectiveness of neural networks in solving complex problems in different domains. Keep learning, stay curious, and I'll catch you in the next video.